Hello, 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 everybody, and welcome back. We're looking now at the 24th question. This is the second last question on our Fermat paper. For any real number x, the floor function here, this is an x where the lines are extending underneath it, denotes the largest integer less than or equal to x. For example, the floor of 4.2 is 4, the floor of 0.9 is 0. So it's strictly rounding down to an integer. Okay. If s is the sum of all integers k between everything between 1 and just under a million, and for which k is divisible by the floor of the square root of k, then s equals. Okay. So the floor of the square root of k. Now that's a bit of a mouthful. I know the floor of the square root of k will be an integer. So we could call it something like n. So the problem is, so the reason I'm going to start off like this, just so you know, is we're talking about these k's here. Well, I'd like to understand what these k's are. It's very hard to understand k when it's trapped behind a floor function and a square root. So instead, if I say, all right, let's let the floor of the square root of k be n, I can use these n's to try to build up k's that work, approaching it from the other way around. Rather than starting with the k's and talking about the floors of their square roots, start with the floor of square root and say, what k's could have this n? So, you know, if it was 3, what things have the floor of the square root be equal to 3? So, for example, 9, because the square root of 9 is 3, and then if you floor that, well, the floor of 3 is already an integer, so it's 3. So that's the idea, and I think if we start there, it might be a little bit better. Now, if n is equal to the floor, then n is less than or equal to root k, because root k could be an integer, in which case it would have to be n. But it definitely has to be less than n plus 1. Root k is confined in this way. So if we square both sides, we can start to get to these n's. Or not n's, these k's. And so then I'm squaring them. So k has to be greater than or equal to n squared, just like that 3 and the 9 that I mentioned a moment ago. But it has to be less than the next square. And we know that n has to divide k, so we're looking for multiples of n in between n squared and the next square. So, for example, if n were 3, we'd have 9, and the k's need to be multiples of 3 in this range between 9 and less than 16, the next square. Multiples of 3 in that range would be 9, 12, 15, and that's it. So there might be n of them for each of these. But how exactly would we work that out? Well, I guess you'd want to do n plus 1 squared minus n squared, and then sort of divide by 3, just to get sort of a rough estimate. So expand the n plus 1 squared out, you'll get n squared plus 2n plus 1. Oh. And you get rid of those, and you'll have 2n plus 1. And when you divide that by n to see how many multiples of n are in this range, you'd get about 2. Just a little more than 2. Just a little more than 2. But yeah, for the 2n there. So obviously n squared is a multiple in this range, but then we get n squared plus another n is the next multiple of n. But then you add on one more multiple of n, that is just before n plus 1 squared. So it looks like actually there's only 3. Let's just double check that. If I went 16, so n is 4 in this case, 16 to 25, 16, 20, and 24 are the only multiples of 4, the square root of 16, in this range. So yeah, it looks like we only get 3 for each n. Okay. So what we're really trying to do is add up all these terms here. And what we can do is we can sort of group them together. So let's make a little chart, I think, here to be clear. So n is 1, n squared is 1, n squared plus n is 2, n squared plus 2n is 3. If n is 2, then we get 4, 6, and 8. 3, we get 9, 12, 15, as we've already seen. 4, you get 12. Now, I'm obviously not going to do a full chart because we'd be getting numbers that are particularly large. 16. We'd start with 16. 16, 20, and 24, and so on. Now, adding these up, this amounts to adding up squares. Also, where do we stop? K has to be less than 1 million. They said less than or equal to 999,999, but that just means less than a million, which is 1,000 squared. So I think the biggest n can be is 999. I'll just grab the calculator really quickly. All those numbers should be in that range. 998001 and 999000, and then the last one 999999. All right, so those are the numbers we are adding up. So adding up squares, there's a formula to add up squares. So adding up squares, 1 plus 2 squared plus 3 squared, and so on. All the way up to... Actually, I'm going to write these as squares. And there's a formula for that. If we were to go up to... what's a letter we haven't used yet? Let's say m squared. The formula for that is m times m plus 1 times 2m plus 1 all over 6. Nice little formula to know. Some of the natural numbers is good. I think I'm about to use that in a moment. M times m plus 1 over 2. And something else that can be useful. I mean, really, any of these powers can be useful, but the natural number 1 comes up a fair bit. The sum of squares 1, every once in a while. Sum of cubes can also be useful. It's m times m plus 1 times m plus 1 all over 4. These are good ones to know. Okay? So what are we trying to do? Well, we're trying to add up 1 squared. If I'm just adding up this first row here, just adding up so many n squareds, or so many squares. So that should be 999 times 1,000 times 2 times 999 plus 1. So that'd be times 1999 all over 6. Okay. Now, the next one we're doing is 1 squared plus 1 plus 2 squared plus 2, and then all the way up to 999 squared plus 999. And if I separate this, it's just the sum of squares again, and then the sum of the natural numbers. Okay. So if I call this number, I don't know, m, what we've really got is m plus the sum of the natural numbers, which I think we should probably also give a name. So 1 plus 2 plus 999. That's going to be 999 times 1,000. M times m plus 1 all over 2. And I'm going to call that capital M, I guess. Okay, but that's this expression here. And then the last one we need to do is 1 squared plus 2 times 1. 2 squared plus 2 times 2. 3 squared plus 2 times 3. All the way up to 999 squared plus 2 times 999. And if I separate that out again, it's the squares. And then take out a factor of 2 times the sum of the natural numbers up to 99, or 999. So then this is m plus 2n. And so what we've really got is m, sum of the squares, m plus n, the last one we just did, and then m plus 2n. And so this is really just 3m plus 3n. Actually, this is kind of cool that they form a geometric sequence. Or not geometric, arithmetic sequence. So I'll get 3 times... They both have 999 times 1,000 in them. Over 6 times... Not 1,001. It's not 2001 either. What was it? 1999. I was... Subtract the 1. There we go. Okay. And then 999 times 1,000 over 2. So if I multiply this by 3, I can divide it by 6. And so then I'll get 1/2, because 3 and these 6s turns into 1/2. I'll get my 999 times 1,000 times 1999 plus 3. Which is 2002, which I can cancel out with the 2 to leave 999 times 1,000 times 1001, which is 1,000 times 999, 999, and then just move the decimal place over. And that should be our final answer. Let's take a look. Are the answers... is it... No, it's not B. C. There we go. So we're going to bubble in C for question number 24. So up next, we have just one more question to go. Let's get a fresh sheet of paper in anticipation for the last question. Question number 25.